Good evening, everyone. How's your week 7?
Very busy.
Okay. Glad to hear that. I hope that also means you have learned a lot and find the content interesting. Okay, one said it's challenging. So how may I help you for this week? Have many of you already done homework 7? And what questions have you got?
We have done, but we don't know how the numbers come into.
Okay, you got a question now?
Jerry, could you go over the questions one by one, just so we wouldn't go hopping from one question to another? That would be great.
Okay, all right. I can do that.
Jerry, the homework was a bit tricky this time.
I see. Yeah, I think more is about the conceptual understanding of the rationale behind instead of any Excel operation. So let's walk through them. We have 3 questions this time, and they are actually they build upon what we have learned last week. Many of the questions are about conditional probability, actually. They are related. So let's see, we have 3 problems. In the first one, we need to make a decision to decide whether we need to make investment at a high level or low level. Because this depends on the market share. So in this question, if we think about what happened last week, we could perceive the market share as a condition. And the event would be whether we invest low or high. And this will lead to different results. Under different market share conditions, this would bring different levels of profit. So it's like an expected value corresponding to a conditional probability we practiced last time. And any difficulties when you address problem 1?
Jerry, for problem 1 for A and B, I know there's a process to it, to doing the math, but I kind of used like reasoning.
Okay.
And figured it out because extremely optimistic means I think it's going to be the best outcome, correct? So whatever gives the highest outcome or yield. That was my understanding from Professor.
Oh, I see. Not necessarily.
No.
Yeah, optimistic is well, unless you share your screen with me, then I can understand which approach you took. But according to what you said, optimistic approach is not necessarily, oh, when I find the highest number on the sheet, then I go with that. It really doesn't work that way. Okay, let me see. Do we need Excel file for this time? Okay.
Jerry, excuse me, do you have a waiting list for people to get in?
No, I don't think so. Whenever they click the link, they will be able to join.
Excellent, thank you.
Okay. Oh, I see. The Excel is only for the simulation for problem 3 then. Okay, got it. All right, let's see.
Jerry, sorry, Jerry, before we jump back there, can we, on problem 1, just to be clear, we're looking for the level, right? The answer is either a low or a high level, not one of the numbers or the dollars or the market share or any of that other stuff. We're really just looking for one of those levels. Is that a full answer if we do that?
Yeah, the answer would be interpreted as whether you should choose low or high. However, this decision is made based on the expected payoff out of the decision. So we do need to calculate the payoff.
Okay, so we need to, so in providing the answer, do we need to show some math? That's where I'm unclear.
Yeah, that's true. Otherwise, you wouldn't have a record of how you made this decision, because there are only two decisions, right? Either low or high. So even if you make a random guess, there's also a 50% of chance that you got it correct. So
I'll take those odds.
well, okay. Well,
Sorry,
let's see. We have 3 questions. So the chance that you made all 3 decisions correct is roughly 1/8. So I wish you best
I won't
luck
take those
on
odds.
that. Okay. Any questions regarding any concepts behind this?
No.
Okay. So
No,
we
can
understand.
you show how to calculate the payoff?
Oh, okay. All right. The payoff is listed here in this table. However, it changes depending on what we condition it on. So, for example, in the part A, we have investment level under extremely optimistic about the market share. So what this means is that an extreme optimistic follows a maxi max, right? Yeah, that's the word, a strategy, and choose whatever decision that has the highest possible payoff. So we compare these 2 things on the horizontal way. So it basically means for this for the decision maker, they will seek under each decision, they would expect the maximum, the best situation. So if the manager chooses low, then it expects that the payoff is this much, because this is the highest value under the low investment level. So we take the maximum of the low row. In a similar way, we do the same for high. That means if the manager decides to choose a high investment level, then they would expect that the payoff would be this much, because compared to all these 3 situations, this 2 million would be the maximum. So then it's a choice between whether we should go with low or high, because we expect the best outcome to happen no matter what under each decision we make. Then we choose the decision that among all the different alternative decisions that leads to the highest best outcome. So this would correspond to this scenario, then it corresponds to high investment level. That's what extreme optimistic means. So yeah, optimistic means whichever decision I make, it will lead to the best outcome under that decision. However, the best outcome under each decision, they vary across the alternative decisions, right? So eventually we choose the alternative that has the highest best outcome. All right. In B, we have a minimized maximum regret. This is somewhat on the different approach to address it. So this regret can't be calculated until we have a comparison, right? We regret because there could be something else that we could have done, then because we didn't do it, then we regret. This is exactly what it means here. When we do regret, we need to take difference. So if we if under a situation we could actually earn more, but we earned somewhat less, but we still earn, that's where the regret happens. However, if we already reach the best outcome, then we don't have regret. However, under this regret, it'll be calculated per column instead of per row. This is because this regret is conditional on the market share instead of the decision. So has the professor illustrated a regret table before?
Yes.
Oh, okay. Then excellent. Then follow the approach, then you will understand all the details. So for example, for regret, if the market share is less than 1%, the best outcome we could make is to invest low, right? But instead, if we invested high, then we would have lost this much compared to the best outcome under 1% market share. That's 300,000. We would comparatively have 60,000 less if we invested high. This is what this is the regret if we invested high under this situation. If instead we invested low, sorry, just 1 second, then we don't have regret. Yeah, any questions?
So Jerry, are you saying for problem 2 or for problem 1B, we need to provide an answer of high or low for each market share option?
No, we compare all these 3 situations, then decides which of them would be best, or
but
would
the final
be
answer is
minimize
either
maximum.
But the final answer is either just high or low.
Yes.
Okay, got it. All right, I'm with you.
All right. Then, any question here?
Yeah, quick question. So when we say the regret, is it minus 300? So instead of losing 300, let me share. Maybe now if I can share my screen.
Yeah, you can.
Okay.
Then I will stop mine. Okay, I'm seeing your screen. Wow, you listed a lot of things. Oh, okay. I think, yeah, I see you made a regret table. It looks good to me.
So is this calculated as 600,000 as the value here? So 0 is, there is no regret on this one, whereas on the high side, is it minus 300 and 300? Because here in this case, instead of losing 300, we have made $300, $300,000. So does it count as 600,000, or how does it count here?
Okay, so here, I think what you were worrying was actually the sign of it. You were maybe hoping to get a negative value to represent regret, but this is, arbitrary. If you see regret, then we should minimize regret, right? If it's a positive value. If we make a sign so that we represent the difference, so it's negative 600,000, then that's the loss, right? Then we should also negative 600,000 would be the difference in profit. So we should, maximize the this negative value, so it's closer to closer to 0. That's the goal. But what we have here is good. Since you give a positive sign of regret, we just need to minimize. Let's see. Yes, minimize the maximum regret.
Okay. So you're saying the 600,000 is the right value?
Yeah, you could feel out that way. That quantifies the regret if the market share is less than 1%, then if we made a high investment level compared to the payoff we could have if we decided to go with low, then doing high would give us this much of regret. Then it's positive. It means we regret doing that.
Okay. Thank you.
All right. Okay. I don't have particular notes of it, but we can. So one of the way we could address it is to make a regret table, just like what we saw earlier. So we have a regret table. Then we do this for each of them under 1 to 4%, the medium market share case. We find that low gives us a higher payoff, whereas high gives us the lower payoff, right? Then it means under this condition, the market share under this condition, we would regret doing high again. So as what you saw earlier in the regret table made by the student, under this situation, we have a regret of 100,000 if we do high compared to.
Excuse me, could you
if
share
we do
your
low.
screen?
Oh, right. I thought I was sharing. Okay, now it's back. So if we move further to the third column, larger than 4% of market share, we do the same thing. But in this case, high gives us a larger payoff, whereas low gives us a lower payoff. So in this situation, we would regret if we chose low instead of high. So this regret would be filled out here as the difference between these two. It'll be 160. 3,500,000, right? Then it'll be the regret. So we have a regret under these cells. Then we choose we minimize the maximum one. So we go horizontal again. Well, I probably should go with a regret table. Do you want me to make one, or maybe
Jerry, can I just ask? So, are you basically just doing the sum of the horizontals in whichever?
Oh,
number?
no. We don't do sum. We pick the max. We choose the maximum level under these horizontal row. Then find the smaller one under these between these two maximum. Could the student who showed the screen earlier show again, so I could illustrate what that means?
Oh, sure.
What's your name?
Mohan.
Oh, Mohan. Okay, thank you. Okay, let's use Mohan's screen, and because he did an excellent job in making the regret table. As we illustrated earlier, now you should understand what a regret table illustrates, right? Any questions on that?
Yeah, still I am confusing about the minus. For example, he did, it's like 600,000. For me, I do, it's minus 300. So because it's regret about 300. So could you give us the equation for that? So, or how you calculate? It's like minus 300, minus 300. So that's why it's coming plus 600.
For that, for the step-by-step thing, I encourage you to watch the professor's video and materials on that. But here we have a very quick way. When calculating it, we simply go column by column. So enter, for example, I just make one case out of the 3 columns. On the leftmost column, we see that if we decide to invest low, then we have a positive profit, 300,000, right? If high, then negative 300,000. So between these two, which is higher? The low decision making, right? So if we instead invested high compared to what we could have earned, and if we invested low, then we lost 300,000 comparatively, right? So this much is a regret. However, to quantify regret, we really put a positive sign of the regret. After that, we try to minimize the regret. That's why you see 600,000 in the regret table. Do you see what it means? That's also why we have 0 under low, because that's under comparison. Compared to low, if we invested low under the smaller than 1% market share case, we don't have regret, because that's the best we could do if the market share is less than 1%. So instead, comparatively, if we invested high, then we would have regretted this decision, because comparatively we would lose 600,000. Is that clear now? So we have the regret table.
Okay, thank you.
Yeah,
I think what's clear, Jerry, is I have lots of regret. I will tell you that. And you're awesome, actually. And thank you, by the way. I think the context that you're providing now was really helpful. And I think it adds, I mean, and Thomas's videos are awesome, but I definitely feel, not everyone, but myself and others are struggling. We need I sent you a message earlier.
Okay.
I think we need more time or more something. I don't know what it is, because we're all like, I think we're grasping at straws, and I think we all kind of threw answers out there. But I don't have the confidence in this homework that I had in all the other homeworks. And I also think it's because of, like Thomas was saying, the gap in classes is so big. So I don't know. I feel kind of like I'm guessing, to be honest.
Oh, I see. That's why we have review sessions.
Yeah, well, absolutely. This is great, but the homework's due tonight, though. So
okay.
Reviewing how I don't feel confident in what I'm going to submit, but that's which is fine though. I think it's and just perspective that I feel like we're all, or some of us are kind of struggling a little bit.
Yeah, I think this.
Jerry, just as I understand the regret table, once we come up with what Mohan is sharing, then because we don't know, one of the uncertainties is the market share. We can only provide a low or high answer. And so our understanding, at least my understanding is that we then added the sums across horizontally, low and high, to come up with the minimized regret based on unknown probability of
Earl, that's exactly what I was asking earlier, because then you do 1.55 million compared to 700,000 on the high versus the low, and then you would pick the one where you have the least amount of regret.
That is the way we understand it, Jerry. Is that, and we just want to confirm that is the right process based on
no, because you mentioned the sum of them. That's where I disagree. So could let's see, Mohan,
Jerry.
right? You are sharing the screen, right? Could you highlight?
So your screen, Jerry.
Yeah.
I think.
Could you highlight the?
You can toggle, Stephen.
Oh,
you can toggle up top for view options. You can toggle between Jerry's and mine.
Oh, thank you. That helps a lot.
If you're using dual monitors, you can actually see them both at the
All
same
right.
time.
Could Mohan, could you highlight the row for high in the regret table? Okay, let's look at this row. So what does minimize maximum regret means? If we chose high, we want to focus on the maximum regret we could have. So under all these three situations, the maximum would be 600,000. We don't add them up. We don't add 600 and 100 because it happens in different scenarios. Now we just need to pick the highest regret under all these situations. For high decision, it's 600,000. Then we move one row above. If we invested low instead, the maximum regret we could have would be 1,055,000, because across all these three situations, this 1.5 million is the largest regret we could have. So compared to these situations, the two situations would be for low, the maximum regret happens at the cell D9, right? 1.5 million. If we invested the high, the maximum regret happens in cell B10 if the market share is less than 1%. Then we just compare these two values. So this comparison goes nowhere beyond what's already shown in regret table. We just compare the maximum value under within each row.
I see.
Then we choose which row has the smaller value. So I can see that probably we would struggle since these procedures requires calculating sometimes column-wise, sometimes row-wise, and sometimes we need to take the maximum of the situation. Sometimes we need to choose the smaller one out of the maximum, the value. So let's see. I think in exam or homework, you're allowed to use your notes, right? So probably you can write your procedure and to record yourself what you've done in each step. But the logic is that once we understand that, for example, optimistic is choose the maximum one, enter the maximum, whereas this minimize maximum regret approach is to find the regret, and then the step 2 would be find the maximum regret for each decision. Then step 3 would be choose the smaller one of the maximized value. So remember what to do in each step, and don't confuse whether it's column-wise or row-wise.
Got it.
About that.
Okay, thank you, Jerry.
Should we move on to part C? All right, thank you, Mohan, for sharing your screen. All right, in part C, let's see. Which invest level should we choose if manager decides to, okay, a third approach, maximize expected value. I think compared to the first two, maybe this is easier since we already practiced how to calculate expected value last time. Now we have a probability associated with that, so we could calculate expected value. We have 30% and 50% and 2%. Remember how we did this last time? We go back to probability, and we learned conditional joint probability, and afterwards expectation, right? We just use this simple but powerful equation to calculate expected value. So have you encountered any difficulty in calculating such a expected value?
No.
Oh, okay, good to hear. Should we move on to part D then? I assume that if you're clear with what happens in expected value, it should be relatively easy. However, what questions could you have in expected value? All right, let me know.
Is it just calculating the EVPI?
Oh, it's different.
Okay.
What's EVPI is in part D, right?
Right.
Yeah, because in part C, we need to calculate expected value under of each decision.
Okay.
It's basically a weighted average of row-wise.
Right.
Okay, then with the expected value, that it goes to part in part D, because in part D we would have to compare two different expected values, then take a difference between them.
So Jerry, is it that simple in that you get the high expected value minus the low expected value, and that's it?
High and low. Yeah, I mean, for part C, we do have two expected values because each of them is associated with a probability, right? So we just calculate an weighted average of the row values. Do you need me to illustrate how it's done?
Yes, could you please illustrate that?
Okay, so let's use one example then. We know that this happens by 0.3, right? This happens, the probability of the second scenario is 50%. And last one would be 20%. Then expected value of low, right? It would be a weighted average of these things. So how to weight them? Just as a weighted sum of all these things. So it means we have 30% weight on the first scenario. That's where we earn 300,000. Then under second scenario, we have 50% weight where we earn 400,000. Then the last one would be 20% of weight, then 4,500,000. This is what expected value means. That's exactly corresponds to what we practiced last time as expected value, because this is a discrete situation. We have probability of each scenario, right? And we times it by the value or the payoff in this case under each situation. Then we have the expected value. Then to calculate the expected value of perfect information, we need to compare two things. So this is the difference between expected value and perfect information, right? But we also have expected value without perfect information. Then this is the payoff. See that these are nothing but expected value, conditional expected value. Then we take a difference. So how do we calculate each of them? We have already done one thing that's based on these two parts, right? So if the market share is let's see. Okay. So if we know something about market share, then it facilitates our decision making. If we know the market share is smaller than 1, which should we pick? We should pick the one that's better, right? That'll be low. If we know it's between 1 and 4%, we would choose also low. But if it's larger than 4, we would choose high, right? So that's where market share influences or affects the investment level. That means if we know something about market share, we would make better decision of the investment level. That's where the information has a value. So if we know the information exactly which of the market share we have, we would experience, then how do we? What would be the decision we make? So if we have perfect information, then it means if it's smaller than 1%, what do we do? We would choose low, right? Instead, if it's 1 to 4, we choose low. More than 4%, we choose high. How to calculate then we just need to take the payoff from it. So to have this expected value of this expected value of payoff under perfect information, it's nothing more than a different weighted expectation. That means we follow very similar formula, but the choice would be conditional on the information, right? So this would be payoff or best, payoff under best decision under smaller than 1% market share. That means this is how much? 300,000. So somehow in the first cell, it's the same as the first one, but you notice that if we move further, then these two parts are no longer different, are no longer the same. So if we move on to the second part, 50%, but this is the situation when the market share is the medium, right? And our medium, we still choose low, so this expected value would be 4. But under the higher market share, however, it'll be different. It'll be 20% of weight as the same, but under this situation, we would have chosen high and got 2 million. So that's why these two parts would be different. So this is how you calculate the expected payoff under perfect information. Any questions here?
That was helpful. Thank you.
Okay.
Yeah,
then, great. Then without perfect information, how would you calculate your expected payoff? Any tentative answers?
You would pick the lowest of each situation.
Oh, someone tried to speak, but it seems the microphone didn't work well. Any other
How about
trials?
now?
Oh, okay. I can hear you now.
Yeah, this is
Did you
Brandon.
adjust this part? Great. Well, I'm
Yeah,
not
you
sure
would
about
just
that.
pick the lowest of each.
Oh, you choose lowest of each? Did you? Was that what you meant?
Yeah, for the not perfect information, the lowest outcome for each situation.
Why? Oh, okay. Then you would be you might be accused of a manager by making the worst decision under each situation. So here, no perfect information doesn't mean that we need to choose the worst outcome. It's to choose the average outcome instead. So remember that we already calculated the expected value. So we do the same for each decision, right? Unfortunately, what Brenda answered was is worse than what this expected value would be. So instead, without perfect information, we would, of course, choose the one that brings us the best outcome, right? This best is weighted, so it's average, the expected value. So we would instead choose the maximum between these two calculated value. Because we already know the expected value of if we invested high or if we invested low, then we we can compare them. Then, of course, as an decision maker, you would pick the best outcome, right? So you would go with the decision that brings you the highest expectation. However, this expectation, as we calculated here, we don't know under each situation, this is not necessarily the best decision if we know something about the market share. So that's why these two expectations are different. Any questions here?
So Jerry, you would have to not only find the expected value for high and low, then you have to plug it into the other equation where you have expected value of payoff perfect info minus expected payoff non-perfect info. Is that what you're trying to say? Or no, we can just take the expected value of high and low and decide which level is the best level. Did I make sense?
Yeah, so I think your question is actually focusing on whether this one is the same as this one. They are not. So if we already know the answers in part C, when we calculated the expected value of low investment level and high, these expectations, as we discussed just now, they were made without the perfect information. So it helps us to calculate this expected payoff under without perfect information. But it doesn't give us the payoff, the expectation with perfect information. That's why we need to calculate further this part. Notice that it's different in the third part, at least.
So this would be for 1D?
Yeah.
Ah, okay. I'm sorry. I got so lost. Okay, that makes complete sense.
Yeah. Okay. Yeah, that's why these two parts are different. Notice that some of them just correspond, but like the third item is different because if we know the market share condition, then we would choose between low and high, whichever brings us the best outcome, instead of averaging across all possible situations.
Jerry, hi, this is Mark here. I think the question is asking how much are we willing to pay to get more information about market share?
Yeah, you're right. But in the lecture, we should also learn about expected value of perfect information, right? This what the cost we would want to pay, the maximum cost we would want to pay, is the difference of the payoff. So if we acquire the information, it helps us to earn more, then we would of course pay something for the information. If with the information it doesn't help us to earn more, then we would not want to pay anything for it, right? So this value of information is determined on how much we would earn in extra compared to the situation without this info. So this equation exactly shows that, and that's why I'm using this to calculate the willingness to pay for information.
And how do you calculate no perfect information? One more time.
Here it is. Without the perfect information, we already did something on this in part C when we calculate expectation. Because with or without the information, we already know the probability, right? But the extra value contained in the information is that with the information, we would know which to choose under these situations, right? That's why these two values are different, and it should be a positive value. So without perfect information, we would, of course, choose the larger one between these two values. So if we expect low, for example, after calculation, this should be somewhere around 400,000. However, this would be somewhere around, 1 million, I would say. So I think the expectation of high would be somewhat higher. Then I would go with the high. All right. Any questions regarding problem 2 and 3? Well, so many words.
Yes, Jerry, can you go over problems 2 and 3?
Well,
Sorry, this was very
let's
challenging
read.
homework.
Okay. Any particular part that you find very difficult in problem 2?
Yes, so do you mind explaining a little bit more about the chance nodes and the choice nodes, exactly when to use them? I think that was my difficulty, was not necessarily drawing the tree, but do you have to have a chance node every time the situation changes?
Okay. I think if you know how to do the tree, then you would get a very good situation and good outcome. But I'm not sure whether there's a better way than drawing a tree.
So Jerry, I think for me, the question on the tree was it's pretty simple that there's a chance node where you're making a production decision. But it doesn't seem to make there is a chance of whether they decide to, or whether they're going to get a patent or not. There were probabilities there, but because there were only two choices, the math didn't make a ton of sense to me. So is there a chance node there at the patent level, or is it just simply a decision?
At the patent part, yeah, we have further trees under patent awarded. So there's also a chance.
So there is a chance at the patent, and then there's a chance at the license.
Yes.
But we didn't get probabilities for the licensing. So that confuses me, unless I read it wrong.
Oh, okay, I see. Okay. Well,
we only got probabilities for the production side of it. So that's the only, well, there and a patent are the only two places where I see chances.
Mm-hmm.
Based on the fact that you need to use probabilities to make a decision.
It seems you suspect that there's some information missing in the question, right? Yeah. Let me
either it's missing or I'm too stupid to figure it out.
I see. Let me read through it, and maybe also with you together, and so we understand what's given in the question and whether we have all the necessary information to solve all parts of the problem. Okay. We know there's a manufacturer doing decision-making whether to continue development of a new promising technology. Okay. So we first know that cost is 2 million. If continued, then a patent is either awarded or not. So there's another layer of decision-making or branches in the tree. And there's also a best estimate is that there's a probability here, 70% chance of the patent. awarded, and 30% that's not awarded. So these two are actually one piece of information. It's just a 70% chance of awarding a patent. Okay, then after the patent is awarded, as the student just illustrated, there's another decision making afterwards, whether or not to license the technology. So here is the licensing, and let's see whether there's any probability given under licensing. If we do the licensing, it receives 25 million in royalty. However, we also produce and sell the technology in-house at a cost of 10 million. Okay, and in this case, there's an additional uncertainty about the demand, and the demand, there's probability associated with the demand. High demand and medium demand and low demand. Under each of this situation with the probability, we have different revenue. Okay, so we have we need to draw a decision tree and risk neutral. It means we just take the expected value, right? Should we continue or not? And should we license it or not, or produce in-house? So here, the license doesn't have a probability associated with it, but we choose the one that gives us the higher revenue, right? If we do the licensing, then the revenue would be 25 million. Instead, if we sell technology in-house, first we have a cost, and then we also have the demand, the revenue due to the demand. So that's where the comparison comes in here. Then we choose whether we do the licensing or sell the technology. Okay. I would just make it be lazy and paste the tree that I have here. So as we walk through the problem, we notice there are a few steps of decision making. We have the ultimate decision making is whether to continue it or not, but there are many steps. First, whether we should continue, and second, whether we should whether we will get a patent or not. There's a probability associated with it. And this third part is whether to license or manufacture. And under the manufacturer situation, there's also 3 scenarios of decision making. Once we understand the hierarchy behind these 1, 2, 3, 4 steps, then we could calculate what happens under each situation. And as I illustrated earlier, the decision making should be made based on the final outcome, right? If we chose licensing, then we would have 25 million as royalty. Instead, if we do the development market, we first pay 10 million, right? Just to make sure, okay. We first pay 10 million, then we expect some revenue out of it. The expected value as what we illustrated in the first question. That's how to calculate expected value. If we know the probability and the revenue associated with each of the outcome, we have the expected value of the revenue. That's why you see this demand value. That's the expected value under all 3 situations. Any questions over there?
No, this is very, very, very helpful, Jerry. Thank you.
Okay, so
I like this a lot.
then okay, glad it helped. But these things has to be calculated further as because licensing also happens with a probability, right? So then we first, through this calculation, it means if we use development and marketing, right? This expected revenue would be how much? 22.9 minus 10, right? This is what happens. We pay the cost. Let's see what's it called. There's a cost, then there's a revenue. So this is the expected value. Then we compare this with licensing. Is this value larger than 25?
Jerry, how did you get 22.9?
Yeah. Yep, I was going to ask the same thing.
Oh, wait, did you have a different one then?
It is 39.9.
34 and something. If you
34.9. It's 34.9 minus
Yep,
10 million.
this will be
Oh, did you
24.9.
say 34.9?
Minus the 10 million, right?
Okay, then it'd be 24.9.
Right. At that level, yes.
Ah, interesting. Okay.
But
Well,
Jerry, I think
maybe
you
I
also have
made
to
a
subtract
mistake.
that 2 million from the original cost for the development cost.
But that 2 million would is upstream, so it applies to both licensing and manufacturing.
I think that's correct.
So it applies equally. So you could do 24.9, or you could do 22.9, but then licensing would only be 23 versus 25. So the 2 million comes off of both sides of the equation, so it really doesn't matter whether you include it here or not.
Ah, well, thanks for explaining. Okay, then if we know the revenue under development market, then we would compare with the licensing royalty, right? With that, we would earn 25 million, right? Okay. If licensing revenue would be $25 million. Okay. Well, they are close. Okay. Then let's see. That means we would go with a license. So if we got the license, if we got the patent awarded, we would choose licensing because it gets us 25 million instead of 24.9. Then this means if patent awarded, the expected value would be the larger between the two above, it would be 25. However, this patent got awarded has a probability. So if we don't know whether the patent was awarded or not, so we chose continue. If continue, then the expected revenue would be 70% of this much. 70% of this much, and okay, but there's also a cost of doing the patents, right?
2 million, yeah.
Oh, thank you. So, this is continued development. Then we would also minus 2. How much would that be? Would this be, let's see, I got, it'll be
15.5, but
right.
so
I
all right,
think
so
I
Gary,
got it right.
this is where I'm confused, because all of those decisions past the patent award would apply equally to both license and develop. So why would we calculate further upstream?
Um,
Does that make sense?
Oh, I see. Because I wanted to, we need to calculate the expected revenue for continuing development. So we need to combine all this information.
To just keep moving it to the left, even though the decision is really on that one branch only, because to stop development, it costs us nothing more.
That's also true, but we need to calculate the expected revenue if we do development, right? That's why we see here. Then we know if we don't do the development, the revenue would be 0. So compared to 0, the development decision has a better expectation. That's why we do want to continue the development.
Right. Okay.
Oh, right. Yeah, you mentioned that. So, okay. Well, I think you're right. I do need to remove the cost of it because this cost of continuing the development would be passed on to all the following decisions. So it'd be better to take care of them instead of not. Yeah, so it should work this way. Any questions in this decision tree situation? All right.
I have a quick question. So with passing on the cost going forward, that goes against what the professor talked about, is you should solve it in the reverse direction.
Yes, you're right. However, in the reverse direction, we already know what happened, right? So for example, if we move to development and market, that means we must have patent awarded before we move to this stage, right? So that means to do the market awarded, we would have to, we would necessarily be on the continuing development branch. That means this cost will happen. So that's why I have these factored in. And in this calculating the revenue, if we already move, if we were to acquire any revenue by doing the development marketing, we need to pay for the cost associated with developing and marketing, right? So that's why also factored in the cost here.
Okay, I think that answered my question.
Did I? Okay. Sorry.
Yeah, I got it.
Yeah. So whatever happened in the upper stream, you receive it in the downstream, right? You won't get rid of it. So if the cost already happened, then you won't be able to have a cost-free situation if you move forward. So I think the strategy to solve this problem is to use the information with all the steps and the lower streams to calculate the expectation under each step, then move backward as what you described earlier. So I think here I illustrated a good process with each piece of knowledge added, then we move backward as if we didn't know it, or under the step there are 2 branches, then collapsing both of them. So for example, between these two branches, we would choose the maximum one. Although one student noticed that there's no probability associated with it. That's why we would compare each of them and choose the one that brings us the maximum probability, maximum revenue. So for example, if we already passed the patent situation, we got awarded of the patent, then the decision is only between whether licensing it or do the development market. So whichever brings us the best payoff, we would choose that. And in this situation, licensing brings us a slightly more revenue. That's why we do the licensing. Then whatever happened in the development, the marketing branch, it won't move upstream anymore. However, in the situation that we do have a probability associated with that, like what happens enter the stream if we move forward after development market, we do need to take an expectation. That means we have a weighted sum of the revenue with the times the probability. Okay, all right. I think we are only one small step away from completing the homework. That's the simulation. How did you like that part so far? Oh, okay. I noticed there are something happening in the chat. Oh, okay. I think I missed lots of comments in the chat. Any questions that I haven't addressed, but you put in the chat already?
I'll just say, Jerry, that, again, this is really helpful. I mean it sincerely. But I need a little more time to digest this because I was on the wrong, like I mentioned earlier, I think I was guessing and now I get it.
Oh, okay. Well, glad it helped.
Yeah, it did really, but I kind of want to learn it as well, not just chuck the homework over. So I'm going to need more time. And maybe I did put in the chat to you and I, maybe this class could use a day or two extra or something extra. I know we're meeting with the professor on Thursday, but
okay.
This is,
well,
this is a lot and it's good stuff and it really is good stuff, but I think it's a lot thrown at us that
I see.
It took this conversation for it to start making sense for me.
I see. I wish I could make a decision to, you know, have a pause button on the process, then you have more free time.
No, seriously, you just tell Thomas that you said, but I appreciate it. You know, all kidding aside, I think the benefit is the understanding, not just the 10 points, it's only 10 points, but this was really helpful. I just need more time.
Oh, thank you. Well, let me know how I can help in this situation then. So
is there a way to extend the homework timeline?
Well, discuss with Thomas then. I have no objection if you do that. But
well, you know,
at the
at
same
one hand, Jerry,
time,
we're all adults. It's only 10 points, but
yeah, if we bomb it, it's one bomb. I mean,
yeah,
think about microeconomics, everyone.
I like that. That's a great call, Earl.
I'm sorry. I have a point of clarification, Jerry. So are you saying that it's not within your control or within your discernment to offer an extension on this homework assignment?
No. So if you, I'm not sure whether at this moment it makes any difference. I mean, if you ever wanted to discuss on the due time, you have to talk to the professor.
Yeah, we'll be
at 8:15 tonight. I doubt we're going to get an answer from him, and it's 3 hours. So
well,
let's just get it done.
Okay. But I mean, this homework is somewhat conceptually challenging, but I don't think it takes lots of operation to calculate anything.
I think, Jerry, though, and I know Thomas is really not a fan of this schedule. I think it's the context of not being in class and not having that. So again, not you're doing, not Thomas is doing. He definitely doesn't like this whole 4 weeks off between visits. But I don't know, like just talking to you made this all work really well for me,
Oh,
but not well enough
okay.
that I can say I got it all. I just need a little more time with it.
Thank
So
you.
I just think no one's doing, that's on this
Okay.
call, and you're awesome. But I just think there's some gaps in the schedule for us to digest.
Oh, I see. Well, thank you for letting me know. And should I move on to problem 3?
Yes, yes,
before we
please.
complain too much about
Yes, please.
okay. So 3 is nothing but a very simple simulation. This simulation in many other classes might be also called as a stochastic process. And the technique we use here is quite simple. It's a random variable generation. However, what I noticed from previous students' homework is many students mistook the benefits of simulation with some requirement of calculating probability. So they overthought the complexity in simulation. Now let's see how we can simplify it. We were given 10 trials with a random outcome and another set of random outcome. So I think in many situations, you might see this in job posting as an A/B test. But I really don't call it A/B test because it's usually we refer to them as experimental design. Okay, so let's read through them to understand what we need to set up in an Excel file. I don't believe we were given the Excel file, right? So we need to construct it.
We were not. You're correct.
Oh, okay, right. So then let's pick up the information from the Excel file so we understand what we need to do. So we have a manager of semiconductor. We run simulation, and there's also uncertainty with it. That's why we have a simulation. If there's no uncertainty, we don't have to simulate anything. So there are assumptions we need to make first. Total cost per month could be anywhere between $150 to $200 with equal likelihood. This is very important. That's why we use the random number generator function. This random number generator assumes a uniformly distributed random variable. A uniformly distributed thing is not normally distributed. They are quite distinctive. It means this function generates anything between 0 and 1 at equal probability. So if or the histogram that we already did in the first 2 weeks, right? If we, for example, define the bin as 10 bins between 0 and 1, we will see that the frequency would form a horizontal line. So that means each bin has equal probability. That's what uniform distribution is. That's also what equal likelihood here means. Because of this, we are going to use a uniformly distributed random number generator. Okay, then we also assume there's something normally distributed. That's the demand. So the demand has a mean of 5,000 items per month and a standard deviation of 1,000, and we also know the price. So here we have 2 simulations we need to do. First, as it says, is the cost that's uniformly distributed because it's equal likelihood. Second, there's a demand that we need to simulate. It's normally distributed. So that means we need to use a normal random number generator. So we have a random generator for 2 random variables, cost and revenue. Let's see, no, cost and demand. However, we need to calculate revenue and profits. These are associated with the cost and the demand, right? Since you are also taking microeconomics, we should be very familiar with the relationship between cost, demand, revenue, and profit. Then we have a random number generator, A to generate the cost and B to generate revenue per month. Then we calculate profit as the difference. Okay, complete the table by reporting mean, max, and average profit per month. Oh, I see. So the random number is already given. Then it doesn't seem we really need to calculate any random number generator at all. Okay.
I think Thomas said we don't have to do, we don't have to calculate any random variables. He gave them to us.
Oh, I see. Okay, perfect. Then if you ever need to calculate these random numbers, then we could follow this instruction to generate random number here. So I could actually do it. Then we have a more interesting outcome. So in random number A is the cost. It's anything between this much, right? So I would calculate it as random number. So this random number is anything between 0 and 1. That's why I have the minimum value here, then have the range of it. That's this would be the cost. Every time I refresh the sheet, the random generator would refresh. So what you can do is, if you ever need to use any random number, you could copy and paste it. Then then it doesn't change in the future. Okay, and copy and paste here. So this one stays. As you can see, generating a random number between some range as uniformly distributed is nothing more complex than using a random number generator if we assign the minimum value and also the range of it. This range 50,000, right, is the difference between 150 and 200,000. All right, so that's how you can generate a uniformly distributed random number. We could also do a random number that's normally distributed by, do we have that? Oh, it doesn't. But you could still generate a normally distributed random number by using normal distribution and also the uniformly distributed random number generator. We need to combine them though. So first we have the normal distribution, then this is X and me. Oh my God. I need to review again.
I think it's norm dot inverse, which professor was talking about.
It was that is correct. That was the inverse that we were.
Oh, thank you. So I need to type inverse. Is that
norm.inv? It's the other way around.
I see. Thank you. This one, right?
Yes.
Then here I have probability. Okay. So here we use the random number generator to generate the probability. Remember that this random number generator gives us a random number between 0 and 1. And we also know the probability is between 0 and 1. That's why we combine these two parts.
But
Any
Jerry,
question here?
for this problem, we're not using the random generator, we're using the number that he provided. for
Oh,
B,
yeah, sure.
Right?
Yes,
So
you're right.
where you have that in your formula, we would replace that with a reference to 0.75 in cell D2 on your screen.
Yes, you are very correct. Cool. Okay, so once we have these calculated, we would fill that in. I mean, in this way, I won't have the exact answer that makes the homework not so interesting. Okay, then we have the cost. Oh, okay, I see. The cost is what we generated in the random number. And the revenue is the same.
So can you go back to your cost calculation one more time? Because that one confuses me.
Cost calculation. This is the cost.
Right.
Oh,
So if we're looking at line 1, and my Excel is not functioning well for some reason. So
oh, I see. Well, maybe I should go back to the beginning. Okay. This might make it much easier to understand. So given these random number that's between 0 and 1, we generate cost using the very similar formula that I used. This would be the simulated cost, and this would be the simulated revenue. So we transform this probability to a quantile on the norm distribution with the known mean and the standard deviation. Any question here? And we know the revenue is 95, the price of each item times demand. That's why we have a revenue associated with a probability that's about to generate the demand.
And Jerry, can we round off this revenue as well? So it'll be easier to determine the profit.
Yeah, you could do that. But rounding in Excel is simply a display issue. It doesn't change the contained value in it.
No,
So,
but
for
I mean, if this
example,
norm.inv, if I round it off, this number for revenue will become 77, not 76.5. Yep.
yeah, like I said, changing these would be only a matter of display. It doesn't change the value in it. As you can see, the value associated with other cells won't be different because the value contained in it won't change, even if you switch to a different display of decimal places.
So Jerry, the reason for the confusion is the professor in his formulas actually used the round function.
That's correct.
In his formulas. So in cell C2, for example, that formula in the professor's example was round, open parentheses, and then referencing the minimum cost plus the random
I see.
number.
No, you don't have to do that. So in the simulation, so for example, in the sheet, we already have these numbers, but the random number can be, it can have as many digits as you want. So you don't have to run anything.
Jerry, can I ask you a question? This is Mark. Do we have to do, hi. So do we have to do anything with the number of products that are produced? It's a 5,000, but with the standard deviation of 1,000. To me, the revenue would be dependent on that.
Yes, you're right. This revenue is generated exactly like that. So how about I show it even more clearly. So this is demand. This demand is generated according to the random number that we are given. But if we want to generate random number, it's also very easy. Then this is the demand, and the revenue would be demand times 95, right? So that's exactly the same thing if you calculate all parts. Here, the 5,000 mean and 1,000 standard deviation comes in how we calculate demand based on a random number. Any questions? Okay. All right. Again, if you ever need to generate a different set of random numbers, simply use this random number generator and paste it back here. But for this homework question, all the random numbers are already given. So your solution would be always the same. Otherwise, in reality, at work, if you ever need to do any simulation, you would want to use random number generator. However, there are also reproducibility issue, right? If you want to transfer your work to another person, once this Excel file is opened again, all these random number, if it uses random number generator, like this function, it refreshes. But in other, I'm not sure whether there's any way to log it, could be, but in other statistical tools, you can set a random seed. So if the seed is set, then all the afterwards random number generation would gives you the same sequence. So you can control some random number. All right. With all these known, we would be easily find some required statistics of part A. So for part A, we have a minimum, maximum, and average. Then we just, I think this should be straightforward, right? If we know the profit. Any questions regarding how we arrived at profit here? Okay.
Could you touch on B also before we end the call a little bit? What are the flaws?
Yes, good question. What are the flaws? I would think immediately that we have only one simulation. I would probably run many times instead of just one simulation. And also, let's see, okay. Oh, okay. I would probably also say that the distribution we use might be not always perfect. So for example, this cost, according to previous understanding, it's between this much and this much. But using equal likelihood, see that it's assumption, right? This assumption might be not a very good way to make, as my understanding is that the cost is also it's not always uniform. We should expect that we would experience some cost that's around the mean more often than those further away from the mean value. At the same time, this demand, if we assume it's normally distributed, it means it takes value from the negative infinity to positive infinity. But in reality, demand can only be a non-negative number, right? The minimum demand we could possibly experience is 0. So in this situation, probably there are better distribution than normal we could use. So we could confine the distribution of demand to be one that only takes positive number. For example, a log normal distribution would give us such property. And I think there's also, in previous exam, I experienced that there are probability calculation associated with such questions. So one bonus question for you. What's the probability of us to have a profit larger than 400,000?
Three and 10.
Oh, great answer. I like it. So because you did it in a simple way, that's good. But since we did the simulation in previous experience, some students overcomplicated this part, that they use the normal distribution to calculate such probabilities. But this thing is nothing more than, for example, if we calculate this probability, it'll be the number of cells larger than 400,000 divided by number of cells total. We have 10 trials, right? And I spotted 3 of them to have larger than 400,000. That's why this probability, according to our simulation, is 0.3. Any questions here? Yeah, so as you can see here, this probability is very rough. So in profession or professional work, if we ever do simulation, it'll be thousands or even millions of different cells generated. Then with that, the probability would be more finer. And because each time we run a simulation, there's also a sampling error. For example, if we go back to this mean of the demand, notice that this demand is generated through a random number generator with the given outcomes, then according to a specific normal distribution, right? So we should expect that the mean of this simulation should be 5,000. However, if we check it to mean, we see that it's somewhat different than 5,000. It's more by 350. So it doesn't exactly match with the intended distribution of the normal distribution. This difference between, for example, in a mean, between the population parameter that we assume, that's 5,000, and the actual mean we calculated according to this simulated sample, that's 5,350. This difference is referred to as a sampling error. If we enlarge our sample size, instead of 10 trials, we run 10 million trials, then the sampling error gets smaller and smaller. However, another good way is to generate multiple rounds of simulation and take mean of all the means. Then it'll be much closer to 5,000. So any thoughts about why we ran simulation in this case? How could we make simulation useful at all if we already have data? Oh, okay. Well, I can provide some situations that you might find such type of simulation to be useful in addition to whatever data we have already collected. So for example, if you imagine that you were this operations manager and you have already collected data on previous monthly sales and manufacturing of the cost, demand, and revenue, then with all the previous data, we could generate these parameters from historical records. We could find that the cost is between this range, and the demand is somewhat close to a normal distribution with a mean and standard deviation calculated. Then we could have the probability associated with profit calculated according to our simulation. Then if you want to generate a report to your stakeholder or those ones on the board, then you could use the simulator to give, for example, confidence intervals or this probability of realizing some threshold of sales or profit. So for example, if you were questioned that you set your goal of next month to be, $400,000 of profit, then you will question, oh, how confident are you with your realizing this goal? You could provide such a probability. That's how you can make this simulation useful. However, many simulations are done more intricately. There could be stratified sampling, so you could generate this profit under many different scenarios or for many market segments. And maybe also all the stores and different countries, you could generate outcome in that level. That's where the simulation also comes in handy, because the finer resolution of data is harder to get. But but usually these parameters are somewhat easier to estimate or receive according to historical data. Then use these information, we could generate interesting probability and also statistics like the one requested in part A of question 3. So you could also give some minimum and maximum and average profit. All right, I think this should summarize our week 7 review, and glad talking with you this evening.
Thank you, Jerry.
Yeah,
Right.
thanks, Jerry. I know you went extra innings again. Thank you so much.
Thank you.
Good night.
Thank you, Jerry.
Thank you,
Perfect. Thanks
Jerry.
a lot.
you.
Bye.
Thanks, Jerry. Have a good night.
Bye.
Thank you.
Good night. Okay.